Hello, this video is a brand new topic about deformation from axial load. So what we're going to do is derive a formula to solve this type of problem. So let's think about a bar. And this bar is anchored in a concrete. And if you have a force P applied at one end, likely this bar will stretch. So we want to know how much has been stretched. So in other words, what's the deformation from axial load? So we want to find this deformation. We call this delta, the change in length, right? Now let's first thinking about it. This is going to be a normal stress. So normal stress is going to this force P. So here, this is force. Don't consider it's a pressure. This is a force. So force over area, the cross-section area of this bar. And then we're going to thinking about epsilon, the normal strain. Normal strain by definition is how much change in length, which is this delta, this deformation we're trying to solve, over its original length, L0. And then we assume this is in elastic region, so we are going to use Hooke's law. So Hooke's law, we know the stress and strain follow this relationship with the slope as E, elastic modulus. And so when we substitute all those in there, so force over area equals E delta over original length. Again, keep in mind we're trying to solve this deformation. So this delta is going to be equal to, so we cross multiply PL0 over AE. That is something PL over AE. It's something we are using often. So thinking about this now, thinking about if you have a bar that has multiple forces on it. So if you have a force on the left, on the right, and I could potentially have a force in some other points in the bar, and in that situation, there are 5 forces here, and assume they are going to balance, so they're at equilibrium. Now ask yourself a question: are those throughout the bar, do they have the same internal force, internal loading? Likely not, right? Because at this section, you're gonna have internal force, and then you're going to have another internal force at this section, and you will have another internal force during this red section. And now you got my points. If it's right here, that's going to be another set of internal force. So in that situation, our P, our internal force, this P here, that's going to be different. So make a note. So P here, that's going to be the internal axial force. Here axial is basically your normal, internal normal force. It's actually different for different section. So that's going to be our internal force. And L, so what's our L here? And L, that's going to be the length for that particular section. It's not going to be the length for the entire bar. It's just for that particular section, because during that particular section, that's how much internal force applied down. That's going to cause that much deformation. So make sure those are internal force and that length in that particular section. And how about A? A, we know that's going to be the cross-section area. That's area for that section. And thinking about this example, this one here, and looks like it's uniform bar. So everywhere, those 4 sections, they have the same cross-section area. But imagine if I might have a bar that's gonna be like this. So at different section, I will have totally different cross-section area. If that's a situation, you might need to consider that changing area. Sometimes you might need to integrate, right, based on the function. Now E is elastic modulus, and if this bar is made of the same material, then that will be constant. However, if the bar is made of different material at different section, then the elastic modulus have to be taken into account. So with all of that said, for this example, you have 4 different sections. We highlighted in blue, green, red, black. So if you want to figure out this entire ball, what's the deformation? So you want to get this formula. So this delta is essentially summation of PL over AE for each individual section. And here we have discussed what those each terms are, and that's very critical. Okay, so very simple concept. We learned about PL over AE in this axial loading. So the next video, we will be looking at example for that. All right, I'll see you on the next one. Bye now.